All right, so we are recording, and here we are again. It is, let's see, July 18th, 2016, and we are here for lectures 9 and 10 of the CENG 3306. I hope you all had a good weekend, and let's begin. So in the first portion of the lecture, we're going to, well, actually in both portions of the lecture today, we're going to be looking at strain. In the first portion of the lecture, we're going to be looking at strain transformation. We have two objectives. One, we're going to convert strain rosette data to a unified state of strain, and then we're going to use strain transformations of equation to determine principal strains, gamma max, the maximum shear strain, theta p, and theta s. So let's do a brief review of normal strain. So review normal strain. A review of normal strain. All right, so the basic idea with normal strain is it is a ratio of the change in length to the original length. So if you have an initial length L naught here, so say we have a sample of material again. This is a review from a previous lecture. Oh, and this lecture will cover sections 10.1 to 10.2 and 10.5 in the Hibbler book. Okay, this is L naught. And then this sample here, we have L naught being the initial length. We have a sample of material under load P. And the sample stretches to a length LF. This sample stretches to a length LF, length final. And the equations that we've seen previously are as follows. Strain equals L final minus L naught over L naught. And this simply equals delta over L naught. And the units for this are, well, effectively it's unitless, but you can think of it also as inches per inch or millimeters per millimeter. And then some other keys here, thing to remember. If we have elongation, which corresponds to tension, that's going to be positive. Elongation is positive and shortening is negative. Shortening is negative. So, review of shear strain. That's normal strain, and let's consider shear strain. While normal strain is based along a change in length, shear strain is based along a change in angle. So we have axes y and x. Oh man, that looks terrible. We have axes y and x. Y and x. Like so. And then we have, let's see, so this is the sample's initial shape. And we have shear like so. So we have shear like this, and like this, and like this, and like this. And then we have the shape. The shape is then changed to via this shear, a elongated shape like this, or a deformed shape like this, I should more likely say. And then the change in angle. We have this angle we're calling beta. and this one gamma 1 and gamma 2. And the equations governing this are gamma xy equals gamma 1 plus gamma 2 equals pi over 2 minus beta, of course, if you're using radians. And if for our sign convention, if beta is less than pi over 2, this will be positive. And if beta is greater than pi over 2, it will be negative. And if it's exactly pi over 2, it's neither positive nor negative because it's 0. Okay, so let us solve for state of strain. Okay, so let's see. So this is going to involve some algebra and math, as many of the things we do in this course, unfortunately, but that's the nature of it. Let's see. So let's solve for state of strain. Now, we start with effectively what we start with are our normal strains. So there is a device called a strain rosette. You can read about this in the textbook, but effectively what you need to know is a strain rosette is a is a tool using strain gauges to directly measure the normal strains on a sample. You can apply this to the surface of you can apply a strain rosette to the surface of an object and very precisely measure the strains of that object, or on the surface of it anyway, when that object is under load. So a strain rosette is going to measure normal strains, but what we would like to do is to calculate the strains at any angle. So a strain rosette measures strains. So let's just write this down. Normal strains are measured in the field, and they are a function of the environment, of the loads, structure, etc. They are a function of the loads, structures, etc. Normal strains are measured in a single direction. So strain gauges measure strain in a single direction, but then from those we can calculate other strains. Normal strains measured in one direction. But a strain rosette is composed of a series of strain gauges positioned at different angles, measured in one direction. And this is just a strain gauge again. And the strain gauge is a device that it is built along the change in resistance of wires based on deformation, and you can read more about that, but strain gauges are just a very common tool used in civil engineering, structural, and mechanical to measure strains in objects. Okay. So, let's see. Let us consider a system here. So we can have X, and just a quick note on deformations. So we're going to have our strains. We're going to have our X and our Y. We're going to measure on the global X and Y axis. But what we want to do is we want to be able to calculate at any X prime, Y prime axis. X prime, Y prime axis. So this should all be old hat to you after last week. This is very similar to stress transformations, except we're doing the same thing with strain. And the equations for this, let's see. Now, I don't know if we want to go all the way through the derivation. I think we'll skip the derivation here. But what you need to, you can read through the full derivation in the book. I don't know if we necessarily have time to work through it in a lecture, but the book does go through the full derivation of these if you are curious. So what you need to know though is the strain transformation equations are as follows. The x strain on any x prime axis is going to be epsilon x plus epsilon y over 2 plus epsilon x minus epsilon y over 2 times the cosine of 2 theta plus gamma xy over 2 times the sine of 2 theta. Then for the y prime, my gosh, that's supposed to be a sigma. Oh my gosh. Or sorry, an epsilon. That's supposed to be an epsilon. Ugh. Okay. Epsilon y prime. That's also pretty bad. Is going to be epsilon x plus epsilon y over 2 minus epsilon x minus epsilon y over 2 times the cosine of 2 theta minus gamma xy over 2 times the sine of 2 theta. And finally, the gamma x prime y prime is equal to negative epsilon x minus epsilon y over 2 times the sine of 2 theta plus gamma xy times the cosine of 2 theta. Gamma xy over 2 times the cosine of 2 theta. And these are found in the textbook. And the equation numbers are, this is equation 10-5. This is equation 10-7. And this is equation 10-6. Okay, state of strain. Let us look at the state of strain. First, let me make sure we're still recording and everything is fine. And we are, so we're good. Okay, let us consider the state of strain. Where are you doing? Okay, let us again consider the state of strain. State of strain. Now, going back here, looking at these equations, just visually looking at them very briefly, you should be able to see there's some echoes, there's some reflections of the stress transformations equations. And that shouldn't be that surprising. These are all built out of just basic trigonometry transforming between coordinate systems. So the equations are not a direct one-for-one substitution. You can't just directly substitute in, sigma for epsilon, but they do share many similarities, so that shouldn't be that surprising. Okay, state of strain. Now, let's see. So let's talk more about strain gauges. Now, your angular strain, gamma, or your shear strain, gamma, is tough to measure. This is very tough to measure with any degree of precision. Therefore, you use strain rosettes. Rosettes, which are 3 strain gauges combined. which are three strain gauges in an array. And each of these have a certain angle. They're each positioned at a certain angle. And by doing this, we will be able to solve the complete state of strain. We will need at least 3 strain gauges, but we can solve. But using these, we can solve for the state of strain at any other angle. So let us consider this. I'm going to consider an arbitrary system of 3 strain gauges. Let's say I have strain gauge A at a theta A, oriented at a theta A, and this is X and Y, of course. Let us say that I have strain gauge B, oriented at theta B, and let us say that I have strain gauge C, oriented at theta C. B and C and theta C, like shown. And what we want to do is we want to write an equation for each strain gauge measurement. Okay, so plugging in into the equations that we had on the previous slide, you will get the following. You will get simply substituting in. We will get, let's see, epsilon A equals epsilon x cosine squared of theta A. Actually, not substituting directly, sorry. These come from, these are equations 10-16 in the text. These are not just, these are taking the previous equations and also doing some algebraic manipulation. Okay, so epsilon A is going to be equal to epsilon x cosine squared of theta A cosine squared of theta A plus epsilon y sine squared theta A plus gamma xy sine theta A cosine theta A. Epsilon b, just similar idea, epsilon x cosine squared of theta b, cosine squared of theta b. Oh, I wrote cosine squared twice. Sorry about that. Sorry about that. Plus, and this is one continuous equation, I just put a cosine squared twice. Cosine squared theta b plus epsilon y times the sine squared of theta b times the sine squared of theta b plus gamma xy times sine theta b cosine theta b. Sine of theta b, cosine theta b. And then finally, epsilon c is epsilon x cosine squared of theta c, just the same idea all the way across, plus epsilon y sine squared theta c plus gamma xy sine theta c cosine theta c. The epsilon y's and epsilon x's are the same in all 3 equations. They are the global. However, what we would really like to have, though, is, so these are equations, these are equations 10-16 in text. However, what we would really like to have is, we would like to have epsilon x, epsilon y, and gamma xy in terms of epsilon a, epsilon b, and epsilon c. So we start, usually what we do is we don't start with the epsilon x's and epsilon y's. What we start with are our epsilon a's, epsilon b's, and epsilon c's, because those are the ones we actually physically measure in the field or in a laboratory, wherever you're measuring them. What we would like to have is we would like to be able to, we would like to have the equations for epsilon x, epsilon y, and epsilon c in terms of these. We have the opposite. Right now we have epsilon a, b, and c in terms of what we right now have are the ABCs in terms of the X, Y, and gamma. But so let's see if we can solve for that. So now we're going to do a little bit of algebra. So let's look at a few special cases. Basically, we're going to use a few special cases and use those to solve for the other ones, and to solve for this system. Okay, so special case. So I'm going to try to squeeze a few notes down here. Theta A is 0 degrees. What if we have something like this? Theta A equals 0 degrees. Theta B equals 45 degrees. And theta C equals 90 degrees. So we have a state of strain. So we have our rosette positioned like this. X, Y, and our strains here basically A is right along the x-axis. Let's see, C is at a 45-degree angle. And B is right at that one. Sorry about that. B is at a 45-degree angle. And C is right along the y-axis. So in this case, what we would have is we would have epsilon x equals epsilon a, epsilon y equals epsilon b, probably actually epsilon c, right? Yeah, epsilon c. And then gamma xy equals 2 epsilon b minus epsilon a plus epsilon c. So these are just a few special cases that we could look at. Okay. So maybe we won't maybe, sorry, these special cases are just special cases to consider. We're not actually going to use these to solve for anything further, but just some other things to consider. Special cases, another special case, when theta A equals 0 degrees, theta B equals 60 degrees, and theta C equals 120 degrees. Well, in this special case, x, y, and so on. So here, we're going to have this. A is going to be right along the x-axis again, and B is going to be at an angle of 60 degrees, and C is at an angle of 120 degrees. C here. Now, in this case, what we would have is epsilon x is going to be epsilon a. Epsilon y is going to be 1/3 of 2 epsilon b plus 2 epsilon c minus epsilon a, and gamma xy is going to be equal to 2 over root 3 times epsilon b minus epsilon a, like shown. Okay, so what if I actually want to get the overall state of strain? Well, if I actually want to get the overall state of strain, the way we do this is like shown. So here's the actual way of solving for the overall state of strain. So those are just a few special cases. But let's say to actually do this, you'll need to solve for 3 simultaneous equations. So if I algebraically solve these equations here for epsilon x, epsilon y, and gamma xy, I will get the following. So if we solve 3 equations simultaneously, what I get is the following. Epsilon a, epsilon b, and epsilon c I'm just going to take these equations here and put them into a matrix form, is going to be equal to cosine squared of theta a, sine squared theta a, cosine theta a, sine theta a, cosine squared theta b, sine squared theta b, cosine theta b, sine theta b, and cosine squared theta c, sine squared theta c, and cosine theta c, sine theta c. This is times, of course. And all of this is times the variables epsilon x, epsilon y, and gamma xy. This is a matrix equation. If you don't know how to use a matrix, probably shouldn't be in the class. Okay. So to solve this, to solve for epsilon x, epsilon y, and gamma xy, missing an x there, and gamma xy, it would simply be the inverse of this matrix times epsilon a, epsilon b, epsilon c. So in other words, epsilon x, epsilon y, and gamma xy let's just call this, for simplicity, I'm just going to call this matrix A and matrix B. I don't want to write that whole thing out again. So let's just say that's the inverse times B. And whatever you get there, that matrix, which corresponds to a single number for epsilon x, a single number for epsilon y, and a single number for gamma xy, that right there is the state of strain at a point. State of strain at a point. And of course, this is for 2D. We're mainly concerned with 2D because that's how you usually physically measure strain. I mean, yes, there are ways of measuring more three-dimensional strains involving, like, say, embedding strain gauges inside the bulk of materials. That's always more difficult. So usually we're concerned with surface strain, two-dimensional strain, where you just slap a strain gauge on the surface of a beam or something like that. Okay, so here, I'll work through an example. So let us consider an example. Here. So say we have a system like this. I have a strain rosette set up as follows. I am told that I have, so all of this is given, that I have theta A, so I have 3 strain gauges, one at an angle of 45 degrees, with a strain measured along its axis of 45 or 450 microstrain. This is just a mu. What that means again is just micro inches per inch or something like that. So then in other words, the strain is 450 times 10 to the negative 6. Theta B equals 90 degrees, and epsilon B is 100 microstrain. And theta C is 150 degrees, and let's say epsilon C, let's let this be equal to 50 microstrain. So quickly plotting this, I can have the following. I can say I'm going to have A, B, and C. B is going to be actually right along the y-axis, and C. And this one's at 45 degrees, 90 degrees, and 150 degrees. So we're given all of this nonsense, and we want to find the state of strain. We want to find epsilon x, epsilon y, and gamma xy. Solution. Solution. (450 microstrain). Okay, so what I'm going to do is, let's back up. I am just going to take these equations here and plug in all of our variables. It really is plug and chug at this point. We just take these equations and plug and chug. It's really not that bad. It's tedious. It is very tedious, but conceptually it's not that difficult. It's just math. Oh, there's a joke there you probably haven't heard before, but that's okay. Anyway, I had a professor at A&M who was notorious for setting up a structural dynamics professor who was notorious for setting up a insane problem with a very complex set of differential equations, and the prerequisite for the course was diffie-q. So he'd set up the problem, then just dust off his hands, walk away, and just say the rest is just math. You can handle it. So anyway, if I ever say it's just math, I'm referencing to a very old joke that you have now just heard. So there you go. So yeah, sometimes I jokingly say it's just math, and now you get the reference. Epsilon x times the cosine squared of 45 degrees plus epsilon y of sine squared of 45 degrees plus gamma xy times the sine of 45 degrees cosine of 45 degrees. Cosine of 45 degrees. And watch your email today or tomorrow. I'll be sending out some notes on the testing procedure for the next exam, or for the first exam, I suppose. Epsilon y, okay, epsilon x again. And of course, any students who are watching this video for review in later semesters, that doesn't apply, obviously. Epsilon x times the cosine squared of 90 degrees plus epsilon y times the sine squared of 90 degrees plus gamma xy times the sine of 90 degrees times the cosine of 90 degrees. Plug and chug. And 500 and 50, let's see, 50, yeah? So this is, I can actually write some units on here, micro, 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 and the bottom of my 5 walked away. 50 micro is going to be equal to epsilon x times cosine squared of 150 degrees plus epsilon y times the sine squared of 150 degrees plus gamma xy times the sine of 150 degrees cosine 150 degrees. All right. So all I have done here is just plug and chug. That's it. I've literally just taken my angles and my epsilons, thrown them into the equation. It couldn't be simpler. Well, I shouldn't say that. I suppose it could be simpler. Anything involving a matrix could be simpler, but, well, actually, this is the simplest way you could do this. I mean, we could be studying another topic entirely. For example, if you want, I could teach you a course in, you know, I could teach an Algebra 1 course, but that's probably not why you're here. So in this case, it couldn't be simpler. But anyway. So now, if I want to solve for this, let's see. I get the following matrix equation. Basically, let's say I reduce each of these to simple decimals. 450 microstrain, 100 microstrain, and 50 microstrain is equal to 0.5, 0.5, and 0.5, 0.10, and 0.75, 0.25, and negative 0.443, or 433. Times epsilon x, epsilon y, and gamma xy. Okay, and there's that. So we now have our full matrix equation, and we're going to solve for each of these. And let me just give these some quick labels. Let's say I call this matrix B, matrix A, and matrix C. C is what we're ultimately after. And solving for this, again, review basic matrix math. Matrix C is going to be equal to matrix A inverse times matrix B. So, in other words, you take the inverse of this and you multiply by this, and you will get the following. Epsilon x, epsilon y, and gamma xy, all of these come together to get 314 microstrain, or micro, let's just say inches per inch or millimeters per millimeter, whatever we want. 100 micro inches per inch, and perhaps 486 micro inches per inch. I once had a 486. Man, I'm dating myself. Okay. So let me actually interpret this. Let me show you on a stress block, or actually a strain block in this case, where what these would represent. So 100 micro, 100 micro, 314 and 314. And then we'd have strain, and note a shear strain, and notice it's going to be positive. Of gamma xy equals 486 micro, like shown. Okay, so that's a quick example. There'll be some like that in the homework, exam, etc. Okay, finally, let me give you the equations for calculating principal strains. I don't necessarily want to work through the derivation of these, but you should have them. So let's just go through this. So first, let us again observe the stress-strain analogy. Stress-strain analogy. Now, epsilon is of course analogous to sigma. Normal strain is the analog of normal stress, and gamma over 2 is analogous to tau. In other words, the shear strain over 2 is analogous to shear strain, or sorry, shear stress. And then let's say, therefore, analogous to stress. Okay, so if you work through it, you'll find that the equations are actually very similar for the principal stresses. So epsilon 1 comma epsilon 2 equals epsilon x plus epsilon y over 2 plus or minus the square root of, again, these are going to be our principal strains. So our principal strains, I want some equations to find the principal strains in terms of the x and y strains. Principal meaning maximum. Epsilon x minus epsilon y over 2. That looks really bad. That's a 2, not a gamma. My 2's can look like gammas. I'm clearly drunk at 9 in the morning. Squared plus gamma xy over 2 squared and gamma max over 2, so the maximum shear strain, is going to be equal to just this portion here, the square root of epsilon x minus epsilon y over 2 squared plus gamma xy over 2 squared. And a few notes here. This is the, again, these are the principal strains, but this would be your R on Moore's circle for strain. And there will be a Moore's circle for strain, which, let's see, well, we can look at a bit in the next portion of the lecture. Moore's circle for strain. And then, moving along. So, finally, for this portion, we can have tan of theta p, or tan of 2 theta p. This is the principal angle, equals gamma xy over epsilon x minus epsilon y, and tangent of 2 theta s equals negative epsilon x minus epsilon y over 2, oh sorry, not derp, over gamma xy, sorry. So as a review, these are the angles where the principal strains occur at, the principal normal strains, and this theta s is the angle where the maximum shear will occur. These will be off by 45 degrees from each other, and in other words, so looking at this, given any normal and shear strain what to take away from this on two orthogonal planes. Orthogonal planes. We can determine the strains on any other plane. Just like with stress, these strains on any other plane. However, we could just, another way we could do this is to just convert to stress with generalized Hooke's law, with a generalized Hooke's law, which leads us to, this is Moore's circle for stress. Moore's circle for stress. So if we have strain, all we got to do is apply generalized Hooke's law, and we will get the Moore's circle. For stress, and we will be looking at that in the next portion of the lecture.